Hi everyone, thanks for joining me today for my presentation, Beyond 3D, How Digital Twins Are Transforming Building Operations. My name is Dylan Underhill, and I'm a BIM and VDC advisor for Trillium Advisory Group. I have a bachelor's degree in architectural technologies and construction management from Denmark, and I live and work in Canada, but I still support projects globally. I started out working on BIM projects when I lived in Hanoi before moving back to Canada to work in an architectural firm. From there, I moved on two of the largest general contractors in Canada before finally ending up at Trillium, where I've been for the last couple of years. My role as a BIM and VDC advisor is quite unique, and I get to work with clients developing and deploying BIM and VDC to their projects or organizations as a whole. Additionally, I still get time to continue my research and development on innovative construction technologies, such as digital twins and reality capture and visualizations. I'm a current member and delegate of the Common Data Exchange Group, or CDX, in North America, and maintain a position in a modular construction think tank here in Canada. I want to start out by defining what a digital twin is, to dispel some common misconceptions. And recently, ISO came out with a digital twin definition in their ISO standard 30173. They say that a digital twin is a digital representation of a target entity with data connections that enable convergence between physical and digital states at an appropriate rate of synchronization. While it's nice to have something a little more official, it's quite open-ended and it's left a lot of room for interpretation. Does the data need to update every hour, day, or year? What constitutes data? What level of digital representation do you really need for it to be a digital twin? In the real world, the most important difference between a digital model and a digital twin is the data feedback loop, as seen here on the right. Having an automated process to support that feedback loop is very important as these data sets get very big very quickly. So let's look at a digital twin as a digital interface. The digital twin is a combination of modules that define what the user is after. I'm going to call them modules, but you can think of these as elements or building blocks that make up the digital twin. The modules you choose for your digital twin are a reflection of the function you require. Every digital twin is going to have a unique data set that powers the feedback loop of information differently. No digital twin is going to look exactly the same as any other digital twin. Modules are typically interactive and visualize the information driving the DT. Having data presented in a processed format like this helps teams make better decisions quickly and can augment the collaboration process. Modules are simply showcasing the data behind the digital twin. So a digital twin is really just those two components. It's modules, or the building blocks, and the data. So if you start with this simplified breakdown in mind, creating a digital twin that functions for your asset is supposed to be goal-based or outcome-oriented. This increases the probability that your digital implementation strategy is going to be more effective and succeed. I want to quickly look at some of the most common modules that make up a digital twin. And the most common one by far is 3D or a BIM model. Geometry and metadata helps teams build the connections between the digital and reality in a very robust way and is sometimes semi-autonomous. 3D geometry is easy to manipulate and is very efficient at showcasing data visualizations. So the framework of a digital twin is already there. We already spend a ton of time creating 3D or BIM models that are designed for the design and construction phase. So they're highly detailed, they're well thought out, there's been a lot of work that goes into them. But for a DT, they're often too high of a LOD, or they essentially contain too much detail. So we have to spend a fair amount of time reducing the model size and reducing complexity to better support what the DT is actually trying to achieve. Models are really fantastic for everything digital. Point clouds are also very common in digital twin products, and are often mistaken for being a digital twin on their own, but inherently they do not contain a feedback loop of information. So a point cloud on its own is not a digital twin. Their complexity to capture can be a little bit cumbersome, but the absolute reality they provide can be invaluable for certain owners or specific projects. Having a combination of point clouds and model geometry can give you the best of both worlds. Sure, they're heavier to process and store, but that could change in the future. Lightweight recreations of contextual information is also very valuable for a DT. Here I'm showing a model that I put together for some 4D animations, but the contextual model can be 2D based, like drawings or images. The goal of the context model is to provide a better overview of the assets, or to track and showcase how the asset is impacting the surrounding areas. It's not something you typically include if you're creating a DT of a small single system or a very specific project. Modules can also be simulation based, showing a visual representation of predictive performance or IoT sensor data live from the asset. These very complicated modules typically help identify asset performance issues like restricted flow in a pipe, or they can become visual guides on replacement strategies. Certainly much harder to set up and more manual very early on, but by far the best way to communicate information. So those are some examples of the modules, but let's take a look at the data side of things. When we look at data for a digital twin is typically broken down into two main categories. We have predictive data and actual data. Predictive data focuses on providing insight into how the asset should operate. It looks at efficiencies and output calculations to create a better product. We see these data sets come online well before the asset is complete in the real world, but it's instrumental into setting up the baseline. Once the asset is complete and functional in reality, we can use sensor data or live data to compare against the predictive data set. This means that both data types contribute to the overall operational efficiency of the digital twin, constantly updating and predicting out what will or should happen as time goes by. This constant feedback loop is the most important piece to the digital twin. All of the modules, the visualization, and animations are simply processed ways to interact or understand these two massive data sets. To add on top, once you have these two data sets working in tandem, you can start adding machine learning processes to process all of that complex data and make better recommendations for your project. If this bridge was a DT, for example, the feedback loop could look something like this. The predictive data set identifies that traffic will increase based on historic information in this one lane at a certain time. The sensors on the bridge capture increased stationary weight and decreased tire and noise vibration. The predictive and sensor data work together to identify the issue and confirm it's real. The DT then gives us more insight into how this issue impacts my financial or operational bottom line. In this example, we could see increased wear, increased emissions from cars idling, and even potentially more car crashes. As the asset owner, I could add variable speed signs that react to the digital twin datasets, or add in reversible lanes that open up to support growing density in real time. The digital twin creates this information feedback loop, which makes an iterative improvement forecast. So essentially, we can make the product better by looking at what has happened and predicting what we should do to be more efficient. I also like to show this example when talking about digital twins for operations. The predictive data set says that each of these pumps should be operating at a specific efficiency, but the sensors inside the pumps have identified that one of these units is not functioning properly. You can see it as the red pump here in the image. Instead of inspecting every component in a complex system, the operations manager can pinpoint the problem. The model is driven by external databases, and the setup for the module begins early on in the project, typically in the design and construction phase. Imagine you're an operations manager or facility management operator, and you pull up your 3D view and you get a direct identification of things you should look at today. It helps take away a lot of guesswork and makes the day a lot more efficient for the asset operator. We can combine these external databases with our trigger-based animation modules, and you could see how a team could interact with their digital twin on a completely unique front. So instead of looking through old manuals or clicking through on an iPad, you can jump into your digital twin in VR or third person or whatever way is best for you. And problems are more apparent, and the process to repair or replace them can all be calculated and rehearsed inside of the digital twin before moving into reality. As the digital twin ages, the predictive and historic data sets become more robust, making the decisions you derive from that data more valuable. To kind of cap it all off, I just want to pull up some actual study numbers to support why digital twins are valuable in the operational phase. Operations and management phase is the most expensive and longest phase of an asset's life cycle by a massive margin. 80% of the project's life cycle occurs in that operation and management phase. The remaining 20% is simply the design, construction, and demolition phases. So there's a huge chunk of money and time being spent in maintaining and operating the asset. So anything that can increase the efficiency by reducing the amount of maintenance you need to do, by extending service intervals, or by providing pathways to smaller maintenance pieces can reduce this 80% number down maybe at 2% every year, which adds up over the lifetime of the asset. Environmentally, in Europe alone, buildings are responsible for 40% of all energy consumption, and they're responsible for 28% of direct and indirect emissions. So if we can run more efficient assets, not necessarily just heavy industrial, but commercial, skyscrapers, all of these things, we can begin to reduce the amount of emissions as a whole that our industry produces. So reduction of emissions is a valuable way to make the environment around us a lot better for everyone involved. And the cost benefit alone is well worth it. So a digital twin at an operational stage gives teams more data to work with, it's easier to understand, and it helps you run a more efficient asset. I want to thank everybody for joining in to my presentation. Digital twins are highly complex monsters of an undertaking, and it's hard to fit it all in one presentation here. Please feel free to reach out to me on LinkedIn or visit our website at trilliumgroup.io. Thanks again, and I'll be around to answer any of your questions.